the mole. The themes that we're going to study in this section is counting by mass, the mole, and molar mass. Counting by weight or counting by mass. So what are things that are sold by weight? Well, candy, rocks, nuts, screws, or any item that comes in large quantities are usually sold by weight. What do these all have in common? Well, they're very small. So why are things sold by weight? Well, it's more practical way to weigh out a bunch of small pieces than to count them individually. In other words, no one wants to sit there and count out each individual piece. What they do is they actually take a given amount, they mass it, and that's the mass that they use in order to determine how many pieces are going to be in a package. Give or take a few. So what do they all have in common, things that are counted by weight? Well, they're all usually small items that take a long time to count, and it's a more of efficient way of counting smaller items by weighing them. And usually, the smaller the item, the more exact the counting is because there's less room for error. So back to chemistry. What does this all have to do with? Well, atoms are so small that we work with billions of them at a time. We obviously cannot count them out individually. So what we do is we count them by weighing them. So the mole. The mole is not a creature that lives underground and is a burrowing animal. It's not a Freckles' ugly cousin. So what is the mole? Well, a mole is 6.02 times 10 to the 23rd units. It's like a dozen. Okay, a dozen we think of as 12. Well, a mole in chemistry we think of as 6.02 times 10 to the 23rd. So if I say a mole of carbon, a mole of oxygen, a mole of lithium, a mole of aluminum hydroxide, a mole of ammonium nitrate, a mole just means 6.02 times 10 to the 23rd, whatever it is, either atoms or molecules. So, taking a look in comparison, if we take one pair of socks, we mean 2 socks. If we take 1 dozen eggs, we mean 12 eggs. Well, a mole of anything is just 6.02 times 10 to the 23rd. Okay, so this is just taking a look at different terminology that we use, okay, when we're dealing with smaller items. Okay, we don't say 12 eggs, we say 1 dozen eggs. If we say 1 mole of a substance, we mean 6.02 times 10 to the 23rd. And look how large this number is. It's 6.02 with 21 zeros behind it. That's a lot. This number is referred to Avogadro's number. He's actually the guy that invented, a guy by the name of Avogadro. Okay, he came up with this idea of 6.02 times 10 to the 23rd using some fancy mathematics. So let's take a look at how big this number is. Well, currently, Bill Gates has about $70 billion, which means 70 times 10 to the 9th. So in order to become a millionaire, Bill Gates would have to earn $33,000 trillion a day for the next 30 years. So it's not very likely. How much water is in the ocean? Well, there's approximately 6 times 10 to the 20 liters, which is equivalent to 6 times 10 to the 23rd milliliters. So in other words, the Pacific Ocean contains 1 mole of milliliters of water, which is a lot. Another analogy is if we take a mole of periods and we line them up side by side like we normally would on a piece of paper, it would equal the radius of our galaxy. So in other words, a mole of periods would be equivalent to the radius, which is the point on the inside all the way out. That's pretty far. So we use the mole as another way of saying this is the chemist's dozen. Okay, so when you think of moles, think of them as dozens. Just as 12 eggs is a dozen eggs, 6.02 eggs is a mole of eggs. 6.02 times 10 to the 23rd molecules of oxygen is equal to 1 mole of oxygen. The number of grams in a mole is different from substance to substance. So just as a dozen pencils and a dozen paper clips do not weigh the same amount, therefore, the mass of moles for different elements or compounds are not the same. So taking a look here, the mass of a dozen eggs or a dozen elements are not the same in mass, but they are the same in number. That is the key. So why do we use moles? Well, oftentimes we want to know how many molecules or atoms there is in a substance. And counting them would just be completely impractical because there's just too many, and even if we're dealing with a small amount, it would just take way too long to count. So we define moles to solve the problem of counting very large numbers of molecules. With moles, you count the number of molecules in the same way by finding the mass, just like you did in the lab. So what can we count using dozen? Well, items, what items it doesn't matter, but usually bigger items. So you have a dozen bagels, a dozen donuts, a dozen molecules, a dozen ions, or a dozen stars. It doesn't matter. Okay, they all mean the same thing, 12. So what can we count with moles? Well, again, the items doesn't really matter, but usually we count things in moles that are really small, such as atoms and molecules. You have a mole of molecules, a mole of ions, or a mole of stars, it doesn't matter, they all mean the same thing, which is 6.02 times 10 to the 23rd. And again, this number is known as Avogadro's number. So why such a large number for a mole? Well, the reason is that so many items in a mole may be because we need to group molecules in very large groups in order to be able to actually see them first and actually get them as a measurable reading on our balances. If we have too few, then our instruments are not sensitive enough, and we cannot find, it's impossible to find the mass of one mole, one molecule, or one atom on our balance, but we can find the mass of 1 mole of atoms or 1 mole of molecules on our balance. So how do we figure it out? The molar mass, which is the mass of 1 mole of a substance. The units that we use are grams per mole. The molar mass is calculated using the periodic table. Each element is equated, the molar mass is equated to the atomic mass in grams of that element. So for example, 1 mole of carbon equals 12 grams. 1 mole of boron equals 10.8 grams. 1 mole of copper equals 63.5 grams. So determining molar mass, what you do is you determine the number of each type of atom that is present in the compound. You find the molar mass of each type of atom from the periodic table, multiply the molar masses of each specific type of atom by the number of atoms, by the number of that type of atom, and then you simply add up all the total molar masses for each atom type. For example, find the molar mass of water. Well, water equals H2O. So there are 2 atoms of H. Each atom of H has a molar mass of 1 gram. And there's 1 atom of oxygen, and 1 mole of oxygen weighs 16.0 grams per mole. So when we add them up, we get 18 grams per mole. So if I wanted to measure out a mole of water, I would measure out 18 grams. Sample 2. Find the molecular mass of glucose. Well, I have 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. 1 mole of carbon weighs 12 grams, 1 mole of hydrogen weighs 1 gram, 1 oxygen weighs 16 grams. When I multiply and then add them up, I get 180 grams per mole. Sample 3. Find the molar mass of aluminum hydroxide. Again, I take a look at each atom type and I figure out how many atoms of each and look up their molar masses on the periodic table. 1 atom of aluminum weighs 27 grams per mole. 3 atoms of oxygen, each worth 16 grams per mole, and 3 atoms of hydrogen with a molar mass of 1 gram per mole. When I multiply through and add them up, I get 78 grams per mole. Last sample. Find the molar mass of magnesium acetate. Well, I have 1 magnesium atom, and each magnesium has a molar mass of 24.3 grams per mole. I have 4 atoms of carbon, each worth 12 grams per mole. I have 6 atoms of hydrogen, each worth 1 gram per mole, and 4 atoms of oxygen, each worth 16 grams per mole. The way I get this, okay, again, I'm looking at subscripts, and I'm also looking at subscripts behind parentheses, and I distribute through, just like I did in the past. When I add them up, I get 142.3 grams per mole, which means if I want 1 mole of magnesium acetate, I would measure out 142.3 grams. Sample number 5. Find the molar mass of ammonium sulfate. Well, I know I have 2 atoms of nitrogen, each worth 14 grams per mole, 8 atoms of hydrogen, each worth 1 gram per mole, 1 atom of sulfur, each worth, or 1 mole of sulfur, each worth 32 grams per mole, and 4 atoms of oxygen, each worth 16 grams per mole. I multiply through and add them up, and I get 132 grams per mole.